forces. So after winning the national rocketry competition, you analyze your rocket at different moments in time. Now question A, you're given that the rocket has a mass of 800 grams and that its net force in the first 4 seconds is 20 newtons upwards. Calculate its acceleration during this time. So given the mass, given the net force, looking for acceleration. Right, alarm bell should be ringing. F net is equal to mass times acceleration, so Newton's second law of motion. And we know mass, we know net force, so we can solve for acceleration. So rearranging our equation, acceleration would be F net divided by mass. Now substituting in the values, F net is 20 newtons, mass 800 grams. Wrong, right? We're in physics, we do science here. We deal with SI units most of the time. So 800 grams is 0.8 kgs. So I strongly recommend the first thing you do is actually in the question, right above any non-SI units, the SI units. So it just makes your calculations a bit easier. So 20 divided by 0.8, get out our calculator. 20 divided by 0.8 is 25. And since we were in SI units for newtons, so for force and for mass, mass kgs, our units for acceleration will also be in SI units, right? Meters per second squared. So in the first 4 seconds, the rocket has this constant acceleration of 25 meters per second squared. Question B. So for each scenario, draw a labeled free body diagram showing all of the forces and their relative sizes. So part 1, it is stationary on the launch pad. So that means it's, on the ground, not moving, it's speed of 0. So I'll use a dot to represent the rocket, and while we know it has mass, so it must have a weight force acting downwards. So I'll use capital W for weight force. If you wrote gravity here, unfortunately you're wrong. You need to write force due to gravity, so like Fg, or gravitational force, or weight force. Right, I'll just stick with capital W for weight force. Now, since it's on the ground and it's stationary, I know that the forces must be balanced. So in the upwards direction, there must be an equal and opposite force. In this case, that would be the support force. Right? The launch pad is preventing the rocket from falling through into the ground. So I'll label that as support. And I've shown that they're equal and opposite by those little dashes, but if you accurately draw it, that is fine as well. Now, are there any left or right forces? There could be a cross breeze, right? But let's assume there's not in this instance. And if you're ever unsure, do state your assumptions. So we could say assume no cross breeze. Now that's a bit excessive for a level 2 physics paper, but best practice. Question 2. Now it's accelerating upwards as it expels fuel. Right, so it's burning off its fuel, it's accelerating up. If it's accelerating, we know that the forces are not balanced, and in fact the net force will be upwards. So our upwards arrow must be greater than our downwards weight. So these arrows are clearly not the same size, because the size of the arrow indicates the magnitude of the force, and we know that the net force should be up. Now what is providing this upwards force? Well, it's the fuel, right? It's the thrust. Cool. Now again, any horizontal forces? No. And if your diagram's not super clear, you can always write next to it thrust greater than weight. Or you could write the net force upwards. Right? Just to show that you know that the forces are not balanced and that the net force is up because it's accelerating upwards. Alright, part 3. At its maximum height. Now what is its motion at its maximum height? Is it accelerating? So let's have a think. So the rocket starts at the ground, it is stationary initially, it accelerates upwards. At some point it runs out of fuel, it keeps moving upwards due to its momentum, and then it's at its maximum height, and then it falls back down. So at its maximum height, its speed is momentarily 0. But that doesn't tell us about its acceleration. So in fact, as it runs out of fuel right here, so no fuel, from that point onwards, it is accelerating down. Even though it's still moving up, right? It's losing speed, and why it's losing speed is because it has mass, and its weight force is acting down. So in fact, the only force acting on it after it loses fuel, and air resistance, but after it loses fuel would be the weight force. And so at its maximum height, it only has the weight force. Would it have air resistance? No. So since it's momentarily stationary, it's not moving, its speed is 0, it won't have any air resistance. So just the weight force. Cool. And this shows that the net force is down because it's accelerating downwards. Part 4. As it deploys its parachute and quickly decelerates. So we're told that the motion is it's decelerating, which indicates that, so we have our weight force, that the upwards arrow will be greater than the downwards arrow. Right, because now it's falling down, the rocket's moving down, so to decelerate means to oppose motion, in other words, accelerate upwards. And now, let's have a think, what's providing that force? So as it deploys its parachute, the parachute is kind of providing the force, but that's not a force. What's the force acting on the parachute to slow it down? Right, that would be air resistance. Or you could say friction. Or even drag. Yeah. So the parachute, which when deployed has a large surface area, and since the rocket's moving, it has velocity, that large area and its speed will make for a large resistive force, right, called air resistance, which decelerates the rocket rapidly. And again, I've shown my arrow exaggerated in that it's significantly larger than the weight force. And finally, part 5, as it collides with the ground and comes to a rest. So let's think. Does it still have mass? Yes, so it's still going to have a weight force. That one's usually pretty free. So what's happening? We have our ground. The rocket has some speed, right? It's moving. And then what happens to the speed as it hits the ground? it loses all of its speed, right? It comes to a complete rest. It might bounce off, but let's assume it comes to a complete rest. So if we've lost speed, that tells us it is decelerating, which, like in part 4, means that the upwards arrow, just move this over, the upwards arrow must be greater than the weight force. And I've drawn this arrow very large because as it hits the ground, it's losing all of its speed in a very short amount of time. And now what is the force that's making it lose speed? We can't just say it's the ground force, right? It has a special name. It is actually the support force, right? Or the normal or the reaction force. So once more, the rocket's moving down, has some speed. As it hits the ground, it rapidly decelerates due to the support force from the ground onto the rocket. And our last question, part C, how does the force acting on the ground compare to the force acting on the rocket in part 5? So we just talked about this one. Now in part C, so the ground is providing that support force on the rocket. Yeah. Now Newton's third law tells us that for every active force, there's a reactive force. In this case, the rocket is providing a force on the ground that is equal but opposite to the support force provided by the ground on the rocket. So let's say ground provides upward support force on the rocket as it collides with the ground. Similarly, the rocket provides, in this case, downwards force on the ground. And I'll put in brackets with the same magnitude. So once more, Newton's third law, equal and opposite reaction force. So the ground is providing a support force upwards, which means it will experience a equal and opposite force downwards. So you may be asking, why doesn't the Earth accelerate downwards? Well, it does. But since its mass is ridiculously large, even though the net force will change very, very slightly, since its mass is just absolutely enormous, the acceleration will be very, very small. Cool. And that is question 1 about forces. I'll see you next time.